Well, good morning. It's a much better weather today. So I'd like to welcome you again to the second annual Space, Cancer, and Personalized Medicine Conference. I'll note that we're doing things in reverse. Yesterday was personalized medicine and cancer, and now we're doing space today. So today, hopefully, today will be just as exciting as yesterday. We saw, I think, yesterday how we were weaving together this story of personalized medicine relates to big data, informatics, gene expression, metastasis and cancer. These topics are starting to come together. So today I think you'll hear from our folks at NASA and others about the value of microgravity research and the effects of that, and how we may in the future start to understand the personalized genetics of astronauts and how that might impact how we actually fly folks to distant places. So I'd like to introduce to you Duane Ratliff, who is the Chief Operating Officer of CASIS. Duane has had over 15 years of experience in space activities, and he really keeps the trains running for CASIS, which is the Center for Advancement of Science in Space. I should mention again today we're at the VCOM Edward Via College of Osteopathic Medicine campus in Spartanburg, South Carolina. Duane.
Tim, thank you very much. This is our second year participating in this event, and I'm really pleased that we have an opportunity to come here again and describe what is, quite frankly, a very unique national laboratory, which has a lot of unique and valuable opportunities for advancing both personalized medicine research as well as, in particular, cancer-based research. What we'd like to do today is try to present to you what the value of microgravity is, particularly from the perspective of research. We've put together two panels, which will be followed by a keynote address, which will hopefully sort of titillate sort of your interest in microgravity in general. The first panel will be one which will address the practitioner's view of the International Space Station as a national laboratory from the purposes of research and clinical care. And then the second panel, just prior to breaking, will be one that looks at what are the actual logistics that are associated with accessing and using a laboratory that, again, quite frankly, is unique. So with that, I will go ahead and get into the introduction of our first keynote address. Joel Kearns is with us today. He is the Deputy Director at the NASA Glenn Research Center in charge of their Spaceflight Projects Directorate. He currently directs and oversees space mission work on solar electric propulsion, cryogenic fluid management, radioisotope power generation, and space communications and navigation. Joel has held several management as well as research positions, not only in NASA, but in the commercial sector, including NASA headquarters, the Ames Research Center in California, at the Marshall Space Flight Center, as well as in the Sumitomo Mitsubishi Silicon Research Center, as well as also Grumman Aerospace. Primarily his research has been in solar materials, semiconductor materials, as well as aerospace systems. He earned his bachelor's as well as his master's degree in mechanical engineering at Worcester Polytechnic Institute. And while there, he designed and manufactured the structure for the Getaway Special Payload, which hopefully, Joel, you'll give us a little insight onto that when you speak this morning. That flew on the STS-40 space shuttle mission. Joel is an associate fellow of the American Institute for Aeronautics and Astronautics, and he was recently awarded the presidential rank of Meritorious Senior Executive in 2009 for his work that he's done at NASA. He's an inventor on 4 patents, primarily focused on single growth technology, and while his approach will be one that's a little different from the clinical care setting, I think you'll be very interested to hear his talk this morning on microgravity research. So Joel?
Thank you, Duane. I'm an engineer who's a material scientist by training. And for many years, I have had the opportunity to work in exploiting low body force environments, microgravity, to address problems in the physical sciences, engineering, and technology development. I've also had the opportunity to work with some researchers who have worked exploiting microgravity for the culturing of cells or the crystal growth of biological or virus macromolecules over the years. So I want to give you a little bit of background about what those research communities have found that they have been able to exploit by using this microgravity environment, or to gain some unique insight in trying to address understanding some basic scientific phenomena in those fields, or in trying to develop unique technologies that can exploit some of that information. And I'm at the Glenn Research Center in Cleveland, Ohio, which is a engineering and technology center, a research center for NASA, which has a long background in either materials development or fluid management in space, or going back 40 to 50 years, even in physical sciences and space exploiting microgravity. This particular research center became involved in looking at the effects of this microgravity environment because early at the beginning of the National Aeronautics and Space Administration, there was great concern about how to manage and transfer cryogenic and room temperature fuels in space for rocket engines and for propulsion. So going all the way back to the late 50s and early 1960s, there was a great bit of work done by NASA working with industry and universities to try to understand this low gravity or microgravity environment and how it would affect the operation of spacecraft, and eventually how it would affect operation of physiological systems, both animals and humans. To the present day, it's gone on to studies of how to contribute to improving human health and performance on long-duration spaceflight missions, working with organizations like NASA's International Space Station Program, human research studies, and physiological studies that are done by universities and industry around the United States. So currently, this particular research center in Cleveland helps NASA implement on behalf of universities and a little bit with industry, but also government researchers, studies related to fluid physics and combustion science, the two physical science areas that are looking to use microgravity, but also in some cases the radiation environment of space or the vantage point of space, to conduct fundamental studies exploiting those conditions. And again, as I said, also looking at how to develop countermeasures to any deleterious effects on humans' health from long-duration spaceflight, again, primarily caused by weightless conditions that we see up in space. There's a wide range of diagnostic and environmental test facilities that have been assembled over the years, which are available to government, industry, and academic researchers around the United States, and are exploited right now to prepare investigations for the International Space Station. In the past, they were used on the Apollo missions. They were used during space shuttles time. They were used to conduct joint American-Soviet and American-Russian research on the Mir space station. And they span the gambit from different types of ways to generate a low body force, a microgravity environment, either by taking packages of experiment equipment, developing those apparatus for some type of specific study, and, for example, dropping them from a great height on Earth so that while they are falling, they are in effect weightless, or by working with providers such as Zero G Corporation that have aircraft that can be flown in parabolic trajectories, where while they're flying on the ballistic or parabolic trajectory, in effect, everything within that aircraft is floating or falling at the same rate. And that can get you this environment of seeming weightlessness for maybe 10 or 20 seconds at a time. Whereas at a building, if you drop a package, you would only get that environment for maybe a few seconds. And then all the way to exploiting rockets that could be bought that would only fly suborbitally, that would get you a few minutes of this weightless environment, or again, going all the way to the International Space Station or other spacecraft where, well, for the ultimate of the International Space Station, you can get days, weeks, and months of experiment time in this low gravity environment. As part of this, this group in Cleveland, working with university partners, has built a large number of sets of experiment apparatus, materials handling, fluid handling, diagnostic equipment, again, exploiting the history that this group has had in doing diagnostics for fluids transfer or just combustion transfer, say for engine development on Earth, health countermeasures on Earth that can be tied back to making physiological or organism measurements in space, and has worked with other groups at NASA and again out in academia to develop experiment apparatus that can be flown, say, on the International Space Station or in the past the Space Shuttle to make measurements in this unique environment. And this group has also supported, with the International Space Station, operating such experiments in space, having researchers either come to Cleveland or other sites to help actually work with the astronaut crews up in space to conduct their experiments, do their data analysis, transport their data back to their home sites so it can be analyzed by the research groups. Again, focusing primarily at this particular location on areas such as fluid physics and transport phenomena, or chemical reactions and combustion, or the physics of fluid transport relating to soft matter, or states such as emulsions or surfactants or colloids or foams or things of that nature. So for more than 30 or 40 years, this low gravity environment has been sought by NASA and others to be exploited really as a new environment that would allow you to elucidate new effects, observe new physical laws that might be obscured by the presence of this relatively large body force field of gravity. And over the period of time that NASA has been working on this, for about 30 or 40 years in the physical sciences area, NASA has sought to try to have a relatively rigorous, peer-reviewed set of investigations selected from around the United States and internationally to make use of this environment, which is usually guided by either NASA's own mission needs in spaceflight or outside recommendations and advice from things like the national academies, and has sought to try to seed through interactions with these different communities, or in some cases funding a vibrant individual investigator, principal investigator community to bring forward ideas for original research. Over the years, NASA has reached out to many industrial partners. There have been many countries that have flown similar investigations or complementary investigations on NASA or International Space Vehicles and worked with NASA, and then tried to take the results of the research when it's published, particularly the government-funded work, which is scientific and published in archival journals, and then try to transfer that into technology, even at NASA, either in NASA and its partners in aerospace, or wider into the American industrial community. And the thing that has changed over the years today, if we look back 20 or 30 years, is that 20 or 30 years ago, the opportunities to go into space to gather this type of data were actually pretty few and far between. The space shuttle, which was an amazing transportation vehicle, could only stay in space maybe a week or two at a time. It took many years to come up with an idea and then perhaps build a piece of unique scientific apparatus that you would bring up on the space shuttle and then make your measurements, bring it down. And if you realized later that you really need to take more data or data under different conditions, you have to start the cycle all over again, try to find a space on the space shuttle to fly in the future, maybe modify your apparatus to take new data. So it led to relatively extended times to actually completely address a question that a researcher might have. What's very different today is that we have the International Space Station in orbit 24 hours a day. It's outfitted with a broad range of diagnostic and scientific equipment, which you'll hear about more later today. And it's available for use by academia and by industry around the United States, working through organizations such as CASIS. And that is very different from even 4 or 5 years ago, before the space station had finished its assembly and was really open for research operations. So many people use this word microgravity. I'm guilty of this myself. I sometimes change the words and I say it's microgravity, or it's low gravity, or it's weightlessness. But what is it when we talk about this term microgravity? It's a condition where the effects of gravity appear to be small or negligible compared to the effects of gravity on Earth. Now, if you just look at Newton's laws of gravitation, gravity, the pole of the gravitational force changes 1 over a power law. So if you think about how far you would have to be away from Earth to really have the effects of Earth gravity drop, it's pretty far away. During the Apollo missions, you might remember, to the moon, when astronauts were traveling 250,000 miles away to the moon, every so often the newscasters would say about 2 days into their 3-day journey, they have left the Earth's sphere of influence and they're now in the moon's sphere of influence. And what that meant back then was that the Apollo spacecraft was going away from Earth at very high velocity, going out to the moon, and eventually we get to the point where it was more being pulled towards the moon by the moon's gravity than pulled back to Earth by the Earth's gravity. That's quite a distance away. But we see when we conduct the experiments in space and orbit that we see people or equipment or animals or organisms floating all the time. And the reason for that is that even relatively close to the Earth, we can set up conditions in orbital flight where everything in effect is free-falling together. So within the reference frame of the spacecraft or the laboratory where the work is taking place, they're all floating, they're all falling, traveling at the same rate. So against that reference frame, they are weightless and they are floating, and they have slight background disturbances disturbing that, but very, very small magnitude. So we feel our weight on Earth when we feel our feet, we feel the force of the ground up against our feet, or when we're swimming, we feel the water up against our body, or whatever is pushing to hold us up. But when we're freely falling, as many of us, maybe some of you have experienced this in skydiving, until you really start feeling the drag from the air, it does really feel like you're just falling, dropping as you are through the air, and you really don't feel any weight. And that's really what you're seeing in space, on spacecraft, for example, on the space station. So Newton diagrammed this out looking at laws of motion hundreds of years ago. His thought experiment was, well, I could show how I could describe the motion of a body being fired out of a cannon, and if I had a very, very powerful cannon, I could shoot the cannonball further and further and further. And eventually, if I put the cannon on a really tall mountain and fired the cannonball really, really fast horizontally, that as I hit a certain speed, the cannonball would fall around the Earth and be dragged down to the Earth at the same rate that the Earth was curving away underneath the cannonball. In effect, it would be in orbit. And you can calculate what that speed should be for different altitudes. You can take into account, of course, the drag from the air, and tells you how high you have to be. And in effect, when you get up to about 17,500 miles per hour, 5 miles a second, at say 200 miles altitude, you will fall around the Earth once every 90 minutes. And if there was no residual atmosphere at that altitude exerting drag on you, you would just stay up there falling around the world once you got up to that speed. And that's why, in effect, we see astronauts and systems float only 200 miles away from Earth. It's because they have this extremely large horizontal velocity. The air drag isn't quite big enough to slow them down fast. So in effect, they're traveling forward and curving down as fast as the Earth is curving down away from them, and everything floats within that reference frame. And it's interesting. You can see people floating around. You can see the great gymnastics they can do, the great use they can make of three-dimensional space, up in orbit. But of course, everything within that reference frame is floating, so that in effect you can discount any effects of body fields for experiments that are being done within that reference frame. Of course, it would be very interesting if it was that simple, if it was simply that all body forces were zero. They're not exactly zero. We normally think of the body force due to gravity. Body force due to gravity here on Earth is quasi-steady. It doesn't change, particularly within the small elevation heights that we experience here close to the surface of the Earth. When you actually set up research where you're trying to understand the effect of body fields or some of the physiological or some of the physical phenomenological effects that come from body fields, you have to take into account any time variance of those accelerations. So if you go up to something like an orbiting spacecraft, you will probably find that these quasi-steady body fields, which are analogous to gravity on Earth, are probably 1/1,000,000th of the size of magnitude of what you'd experience on Earth. And that's where the term microgravity comes from, 1/1,000,000th of an Earth gravity. There are other things that can happen also. If you're physically in a system like a vehicle, the vehicle might be flexing. It has mechanical modes. Maybe it's going into and out of the heating from the sun, the cold when it's behind the Earth. It can't see the sun. The vehicle flexes. There'll be some low frequency, in effect, body fields that are generated just from the movement of the vehicle in and out. You could have the vehicle, your platform that you're doing work on, have pumps on it to circulate coolant. That might put a different transient or periodic force through the vehicle, which things in it and its frame would view as an acceleration. The good thing is that many physical phenomena that need to be studied, if they need a long duration body field, many of them are either immune to these higher frequency effects of varying accelerations, or if needed, it's relatively straightforward to build isolation or either passive or active isolation countermeasures. So for a particular study that needs to be done, You can isolate the particular equipment or species or material that's under study away from these more higher frequency effects. So over many years of work, what's been found is for many, many systems that seek to be studied, particularly in physical sciences, you can in fact isolate out these transient effects and focus more on the quasi-steady effects and the effects that are really truly an acceleration body field, which you probably someone may have some interest in eliminating those effects to study something else in more detail. So, pardon me. Why use microgravity? There's a large number of studies that have been done. Many of the reasons to use microgravity is to try to remove this overwhelming effect of the gravitational body field, which is either adding to, counteracting, or non-linearly coupling with some other effect which is of greater interest. For example, working in a gravitational body field will generate buoyancy-driven convection in fluid systems, which can obscure other types of fluid transport. You will not get anywhere, you will get 1/millionth the magnitude of the convective influence from the body field by working in orbit as you would on Earth. So that might elucidate some other mechanism which, particularly in small scales, could be obscured for studies that would be done on Earth. You could eliminate effects of hydrostatic pressure. If you're dealing with a fluid or a soft system in a 1G body field, you'll get a lot more force on the bottom underneath the pack of material than you do at the top. You'll have conditions when the body field's reduced where you won't see that hydrostatic pressure. You can have systems where there's multiple components in them, in an aqueous solution or some other fluid where sedimentation will cause settling due to the body field and give you some stratification of properties or behavior. If you do those studies in a low gravity environment, you won't have that stratification. You can look at true averaging, true physical system averaging by exploring the behavior of the system in those conditions. So this has been exploited for a large number of studies over the years. Things like in my field, looking at kinetics and transport in phase transformations and crystal growth or solidification. It's been used at looking at triple point phenomena, which is looking at thermodynamic phase coexistence regions where fluids such as gases and liquids and solids can coexist to try to really understand the behavior of materials. It's been looked at for manufacturing processes like sintering in metals and alloys and ceramics. And as I'll show later, it's been looked at systems that are very chemically and transport dynamics, such as combustion. And it's also been used as a way to try to understand very subtle effects which under large dimension conditions, very large length scales might be obscured by these body fields, but as we move to smaller and smaller length scales will become more important. So gravity can affect fluids in a variety of ways that have been reviewed by many researchers as well as the National Research Council. And in the past 20 to 30 years, people investigating fluid physics and transport or fluid dynamics or fluid mechanics studies have looked again at this near elimination of buoyancy, convection, sedimentation, or hydrostatic pressure. And as an example of that, a very simple example that can be solved using classic techniques that don't require much numerical simulation. If you look at a very day-to-day example where you have a vertical plate, say, that's at a high temperature, that's in air, and this could be a cup of coffee or it could be a human body, standing in a room in air. You can draw out all the mass transfer equations for continuity. You can draw out the momentum equations for the fluid. You could balance the energy equations if you were interested in learning the temperature distribution, for example, in this air, which might give you an idea of how heat is taken away from the hot body that's in the room. And you will see when you look at them that they're coupled, particularly because of this effect of gravity. If you simplify the momentum equation, the convective transport equation, which is looking at velocities in this two-dimensional setup, the velocity that's horizontal is v and the velocity of the fluid that's vertical is u, you can see here that as you further simplify the equations, the solutions you would get for temperature and for velocities are actually coupled one to the other, and they're coupled because the density of the fluid changes with temperature in most practical problems dealing with air, water, oils, even though the fluid itself is incompressible. So as you start relating temperature and velocities together, it's not really a trivial problem to solve. Even setting up this simple problem requires a numerical solution It requires setting it up so that it is, to make it more broadly applicable, non-dimensionalized by dividing many of the variables against reference numbers. And when you do, when you solve even this simple case, you can see that the solution is very dependent on the relative contribution of the body field, that is gravity and density together, that will actually give you the temperature distributions and the velocities of the fluid that might be of interest. Now, most problems are not this simple. This problem is really a classic problem. You still need numerical integration to solve it completely. But for any practical problems that include moving systems, moving solid systems, that include unusual boundary conditions on the solid, that have unusual fluid properties, that include aqueous systems, reacting systems, these problems become quite complicated to solve in using the acceleration body field as part of the environment, which meant that for many, many years there were many questions about whether these governing equations, these basic governing equations, were really complete or not, because there was such error introduced in the experimental measurements, and the numerical simulations were so complicated that this was the focus of a lot of work exploiting microgravity, say 15 or 20 years ago, was to look at some of these very basic momentum and energy and composition transport equations, run the experiments without gravity as generating a large body field, and see whether the results were different. In many cases, the results were predictable, but in some cases they weren't, and they led to new areas of research, particularly in very complex fluids that are either things like colloids, or where there are phase changes going on, or where there were multi-component systems like emulsions or things of that nature, where studies are still continuing today to just try to understand what is the governing physics really underlying this when gravity is removed. A classic example is the combustion process in fluid transport, where you have a chemical reaction taking place that is also changing this temperature environment and driving fluid flow. And one of the classic demonstration experiments in space that goes all the way back to Shuttle and Mir is to conduct candle flame burning in space. And it jumps out the difference in the convective and heat transfer effect when there's large-scale transport versus when everything's by diffusion. If there's no really body force field-driven convective transport, pretty well all the heat and mass transport's by diffusion, as you can see on the photograph all the way on the right. And when this was first, I can tell you, for example, that when this was first just done as a demonstration experiment, there were many workers in the field that said that the flame would not exist, that once it collapsed into diffusion transport, it would automatically be extinguished. And that was the general understanding at the time for what the thermal physical properties were and what that meant to just have purely diffusive transport. Workers have found, even in this simple system, that the flame can continue to propagate and grow and consume its fuel, even though it's strictly got purely diffusive conditions going in and out of the flame front area, which was a big change to people's understanding of even the combustion phenomena, very simple combustion phenomena. Again, for the International Space Station that's in orbit today, it's a large working laboratory. It's got skilled staff on board that learn how to operate experiments that are conceived by investigators on Earth. It's got multiple laboratories in space that are outfitted with equipment. It's also got places where experiments, if for some reason they shouldn't be done on the inside where the workers are, they can be done on the outside of the space station, either to get exposure to the environment there, hard vacuum, different level of radiation, vantage point energy from around the Earth. And it was recently completed assembly a few years ago, and now it's focusing on exploitation, utilization, and research. And it's outfitted with a large amount over many years of NASA industry and industrially developed research apparatus in many different fields. For example, there's a suite of freezers that can freeze samples to various low temperatures, refrigerators, coolers, optical microscopes, furnaces for heating, for treating equipment, and then a large number of specialized experiment facilities, suites of equipment that were optimized to do particular sets of research experiments for particular campaigns and themes. And for example, just last week, studies were done using the microscopy equipment up on the International Space Station to just look at behavioral studies of nematodes as a way to start looking at exploiting the optical microscopy experiment in certain investigations that was originally designed for physical sciences equipment, and make it available for biological science investigations. The equipment that is there is always being assessed in response to the needs of industry and academia for upgrades or increased capabilities in the future. For example, much of the optical microscopy equipment that's available on station is currently planned in the years coming up to be changed either to, for example, laser confocal microscopy equipment to look at surface roughness and topography or elevation maps, or to be able to manipulate very small specimens using things like laser tweezers to move, to physically move specimens around under magnification and study and see how they react under that environment. NASA and industry use the International Space Station for a variety of different needs. One is what's called NASA utilization, which is really focused on either NASA's traditional funded in academia basic scientific investigations, or NASA's need to develop technology or gather knowledge to aid future human exploration planning, such as to improve human health on long-duration missions. The U.S. National Lab, which is the whole suite of equipment on the space station, which is open for use by academia and industry in the United States, is managed by CASIS, who's putting on this workshop with organizations this week. And this is available to support U.S. national needs for basic and applied research in many fields. And then, of course, also there's great international utilization. International organizations or nations have supplied equipment to the ISS. In some cases, they've supplied whole laboratories. And then there's bartering and trade to either use their equipment or use their laboratory facilities. NASA personally sponsors selected certain types of research which is conducted on the ISS outside of the work that is engendered and brought forward by CASIS, focusing mostly on space biology, on human research, which is health countermeasures for astronauts so they can explore further than in the future than just nearby Earth in orbit. And then in more academic, very basic studies in physical sciences in certain areas. In the physical sciences area, traditionally focus has been on fluid physics, on these combustion studies. In fundamental physics, such as the critical point phenomena, you may also have read about studies that were recently approved to look at things like Bose-Einstein condensate behaviors or atomic clocks in low gravity. In material science, studies of materials processing, structure properties, and performance relationships when things like buoyancy-driven convection are removed during materials processing. And then in areas like biophysics, either the growth of biological macromolecules like proteins or viruses that can be used for structural biology studies, or making unique benchmark biomaterials, or understanding fluid physics specifically aligned to biological systems. And also in complex fluids such as colloids, liquid crystals, foams, gels, how they are synthesized, what the basic relationships are of setting up such processes so that they can be brought to completion. Now, this particular site, years ago, that I come from, the Glenn Research Center, was actually originally called the Lewis Research Center years and years ago. And this site actually developed the first microgravity fluid physics experiment, which flew on the last Mercury mission way back in 1963, to show you how long people have been working in this area. They had been working simply to look at fluid behavior in space, how fluids would move, what was the real balance of say, thermal capillary effects in moving fluids if there was no big body field behind the fluid. And again, back then, that was considered very, very important and new for just fuel management or oxidizer management in space. And even more recently, these types of basic fluid studies are still underway, where, for example, by eliminating that body field, we can look at the effects of surface energy, surface stress on solids and fluids, and we can see how we can set up conditions to deliberately move fluids around, for example, for a technological utility in space, by setting up different conditions of pressure or different surface interfaces so that we, even without a body field, we can transport fluids around. From NASA's point of view, that's really interesting for the engineering of spacecraft. From industry's point of view, it could be interesting in how it identifies under particularly very small scales how fluids can be manipulated, under what gradients or fields they will naturally move under. Again, particularly under small scales where gravity-driven effects become less important. And again, surface tension effects in space become much more prominent. If you know that if you have a body that has a certain surface energy, that if it's a fluid system where it can continuously deform, if it wasn't under a 1G body field, it would adapt the spherical shape, because that would give you the minimum overall energy of the system. The area of the sphere is the smallest area that you would get in a fluid shape. And given whatever the surface energy was of the fluid to the atmosphere it was encased in, you would end up getting a spherical shape. Of course, you don't just get a sphere. If you start manipulating it with external forces, you can end up getting other shapes. You can end up getting oscillations and movement. And by doing that, you can get further insight into thermophysical properties, not just the surface energies, but viscosities and higher order terms related to for example, internal momentum transfer, things of that nature. Again, very, very basic things to look at fluid physics and the transport phenomena of systems. And again, and early on, these were looked at as very basic studies that were looking at very, usually one or two component systems to try to understand very basic phenomenological governing equations. Now they're being extended to more complex systems where there's even more nonlinearity and more coupling, particularly eventually moving to very complex life systems or biological systems. Some things that we see on Earth all the time behave very differently under low gravity. For example, if you have two-phase flow in a pipe, you've got a liquid and you've got a vapor, as you can imagine. As it flows, you will probably get most of the fluid at the bottom in a gravity field and all the vapor in the top. You will really see the effects of the surface energy and viscosity, and you see the different pockets form under low gravity as you transport that fluid. Again, some of the relationships that were developed for this through low gravity experiments the last 15 years were very different than what people expected from the original simplifications of very simple one or two dimensional systems that were developed decades ago. And in a phenomenon that many of us see, you know, if you cook, if you use boiling to boil things in your kitchen or to prepare samples for sterilization, even the phase transformation of boiling is very, very different because of this change in convective transfer if you conduct it by removing the body field. On the right, you see the microgravity specimen. On the left, you see a normal 1G earthic specimen. And of course, in 1G on Earth, when you have the phase transformation at the hot point in the bottom, which takes the fluid from liquid to its vapor phase, it starts great convective mixing. It starts changing the temperature. It transports the species all around the container. If you're just dealing in microgravity with the body forces removed, everything just really occurs from the bottom up, and you see almost this progressive wave of a phase transformation and boiling. Similar studies have been done for soft materials, complex materials such as colloids and rheology, to look at understanding the mechanisms of phase transitions, anything that balances transport and kinetics and nucleation, the formation of non-crystalline phases such as glasses in these systems. And industry has been working to try to understand these processes and how to exploit, for example, phase separation rates to develop underlying theories to either set up new types of soft matter or to predict product shelf life, which is work, for example, Procter & Gamble is doing. It can also see the steps in the maturation of how structures form, solid structures form from these precursor liquid phases, and it might be able to shed some insight into the reaction kinetics and how they work with the transport aspects. In some cases, conditions were set up that were never observed in a 1G body field. For example, using colloids as an agglomeration of hard spheres as a model for crystallization. 20 years ago, before the first experiments on Mir and the space shuttle, crystallization of complex morphologies was never seen, but starting with work on the shuttle and Mir, it was possible to set up, in effect, dendritic or unusual morphologies of these colloidal crystals in space that were then used to validate models for their formation. And this has now been extended to more unusual geometries, very complex geometries, to make either benchmark materials or to make or to provide tests of mechanism formation. There's a great interest now in extending beyond emulsions and colloids into foams. This is an example of work being done internationally between European nations and American researchers to look at stability of the synthesis of foams, to look at different foam structure, how much is open cell versus closed cell packing, and then to put together relatively simple benchmark experiments under different conditions, fly them in space, and compare them to the models. Now, combustion is very important for NASA to study because it's used to propel spacecraft, and it's also used in some ways to generate life support system components like oxygen as a backup system in spacecraft. But of course, it's generally important for the United States to understand how combustion works, getting back to energy efficiency, what its hazard potential is, either in fires on ground or in industry. But it's very complex, as we talked about earlier with the example of the Campbell flame. And the biggest challenge to this discipline is that combustion, in a way, has been so pervasive so long in everyday life that people outside the field believe it's relatively well understood, where a lot of the basic phenomena, at least to be able to use those basic phenomena to predict behavior in detail, are actually not complete yet. So people have studied solid combustion, fluid combustion, gas combustion, liquid combustion in space over years, trying to match the behavior that they see in tightly controlled experiments to the basic phenomenological model. And particularly on space station for the last 5 or so years, droplet combustion experiments, combustion of this non-body field smeared spherical drops that can be very well modeled analytically, have been used to try to test theories against this ideal geometry to validate the transport and the kinetic models. Again, as you can imagine, this is something that's only possible to do in very short time frames and very small samples on Earth, but it's possible to do this routinely up in orbital flight where you can remove this body field. And this has been exploited recently to make very new insights into the combustion process. This is a video of a standard droplet combustion experiment done on the International Space Station. They were measuring how the drop would expand, how it would burn, when it would extinguish. And what the surprise everyone got in this particular set of conditions is that after the drop had theoretically extinguished, by looking at it long term under different visualization techniques, they were able to determine that the drop was actually still burning, although it wasn't clearly visible to people that was operating the experiment. This was something that was not predicted by a lot of the basic phenomenological equations that were set up to model this kinetic and transport experiment. And this has led to a whole new area of study now in combustion research, which will be exploited on the space station in years coming up, and has a few ways that this could be transported into managing combustion processes or combustion process in motors and industry that people are looking at the potential technological implementation. So I've spent a little bit of time talking about physical science experiments on the space station. I wanted to say a few, and on shuttle and on Mir, and how people have used those to try to either understand governing laws or make benchmark samples that can be used for study or test particular theories. NASA works with industry and academia to look again at human spaceflight, performance of humans in space, and look at the limitations to humans operating in space or long duration flight, particularly as we send crews way beyond Earth orbit back to the moon, to Mars, to other places in the solar system, with a great deal of emphasis here on phenomenological and clinical studies on the effects of radiation or physiological changes due to microgravity, due to changes, say, to the human immune system, or say due to things in my area, phase transitions for looking at renal stone formation, or even in areas of crew behavior. And although that's not my area, one area that the particular group that I work with does work in is exercise countermeasures to look at how the crews can exercise to maintain physiological health when they're on long duration missions. And the space station, since it's always there, can be used as an analog or a test bed for long duration missions, and try to develop either the equipment or the methodologies that allow the crews to maintain good health over long durations in space. And here you can see crew members in space training on Earth and also up in space, and space on the top, and then doing studies on the bottom on Earth for exercise as countermeasures against any deleterious effects of long duration space flight. Now, although many studies have been done in the past to take, say, cells or organisms or models up into space and observe their effects when subjected to microgravity, there's a new emphasis now to try to couple these really basic studies of fluid physics and reaction to biological systems. It's kind of an intersection or an iterative area of trying to take the data that's been accumulated in microgravity and focus it more on biological system studies, and particularly to look at fundamental questions about how fluid physics and transport might affect the response of organisms to these differences in gravity or other environmental factors. Some studies have been done of benchmark studies. For example, Hammond published results of a space lab mission in the late 1990s looking at early work on gene expression in relatively simple apparatus, simply to look at comparison studies where there was a body field and where there's not a body field present. And others have extrapolated these studies, which have also been published, which are available in the literature. Now people have moved away from, many workers have moved away from simply looking at comparison or benchmark studies to try to use this type of system to propose to either generate or refute or confirm the hypotheses for why the systems would be behaving this way. So I wanted to try to give you a little bit of background on how microgravity has been exploited to do scientific and engineering studies in physical systems. There's a lot of areas in microgravity fluids and in combustion and in soft matter systems that have led to quite a bit of results in the literature. I remember one year in probably in the early 2000s, even before Space Station was doing a large amount of research, that there was probably 500 archival journal or peer-reviewed articles that came out in one year just talking about the results in these three areas in fluids and combustion and soft matter. And that NASA and its international partners have made this large investment in the ISS, both for our use and the use of this wider community, by working with groups such as CASIS, broad areas in the United States, in your field and other fields, can make use of this really unusual low gravity environment when you have unique questions that need to be answered to your field. And there's a large number of people at CASIS and at NASA that are available to give you support, to show you what has been done before, to show you how other researchers have attacked trying to exploit this environment in all these different fields, which on very basic may look like they're very fundamental, but they all really, in some ways, can be linked back to biological systems or models or physiological studies and eventually maybe clinical studies. So I hope this gives you a little bit of background and some context, and I'm available for questions here or later on after the conference. You have my contact information. Thank you.
Thank you, Joel.